Okay. Actually, one minor correction. It's not going to be me. Me and my colleague Sreeram Potluri, who actually did most of the work for the GPUDirect RDMA, will be presenting this talk. So we'll be going over like an overview of what MVAPICH2 offers, like since supercomputing, what all we have done, what are the like nice performance benefits we get by using MVAPICH2. And finally, we'll also look at the current hot topic, GPUDirect RDMA. So, as we all know, clusters have been gaining popularity over the last decade. If you can just take a look at this graph, it's more than apparent. Almost 80% of the top 500 supercomputing systems are made up of clusters. And among this 80%, InfiniBand demands a very large share. As you can see, almost 16 systems in the top 50 are InfiniBand. MVAPICH and the MVAPICH2X software are like a pretty popular MPI library for use in such supercomputing systems. We recently released MVAPICH2X, which is which has support for hybrid programming models like OpenSHMEM.MPI. So it's available for download from our website. So please give it a shot if you are interested in hybrid programming models and extracting peak performance from it. So recently we made the public release of the MVAPICH2 1.9 and MVAPICH2X 1.9 softwares. These have various major features and enhancements when compared to the previous releases. For one, we do support all of the MPI3 features. We also have support for intra-node, let's say, cross-memory attached communication. This provides extra flexibility for intra-node communication. Let's say now you have shared memory, like kernel-based copies such as Limit, as well as cross-memory attach. We also have support for Scalable checkpoint restart. This is a library from Lawrence Livermore National Laboratories. This supports two different modes of checkpointing: application transparent as well as application guided checkpointing. We introduce support for scalable multicast or scalable broadcast based on UD multicast. We'll be showing some performance numbers based on that taken on Stampede supercomputing system. We've also done several improvements and tunings to the library. And we have also revamped the build system. I think this was one requirement a lot of users were asking whether you can do a parallel build or not. So currently we do support that. MVAPICH2X supports hybrid programming models like MPI plus PGAS, as I mentioned. So we have several papers published already along this direction. I'll go over some sample performance numbers as well here. Now, this is how the talk will proceed. We'll first go over an overview of the design and some performance numbers from MVAPICH2 and MVAPICH2X in various nodes like intranode communication, non-blocking collective communication, fault tolerance, hybrid programming model, things like that. And then we'll head on to how we can use MVAPICH2 for GPU clusters. Finally, we'll conclude with a few remarks. By the way, please feel free to interrupt me at any point if you have any questions or if anything is unclear. So this is a standard one-way latency. So here we see how our software stack has evolved over the years and how the performance is for the MVAPICH software stack for various interconnects. So here we look at the latency for small messages and large messages. As you can see, MVAPICH2 performs the best, and the best numbers are obtained with ConnectIB dual FDR, which is one of the newest products from Mellanox. And at the bottom, we show on what all clusters these numbers were taken, so that if you want, you can try to reproduce this on a similar system. These are again the unidirectional bandwidth numbers for various versions of MVAPICH running over various interconnects. As you can see, we are almost able to achieve 100 gigabits per second bandwidth with Mellanox ConnectIB dual FDR adapters. We have also done several enhancements for scalability and to deliver performance at really large scales. So one such enhancement is the inclusion of support for XRC and the hybrid mode of communication. So as you guys might know, InfiniBand has support for RC, UD, XRC communication. However, just using one transport protocol might not deliver the best performance. So here we study how by intelligently switching between RC, XRC, and UD, we can extract best performance from micro benchmarks as well as applications. So we can see that by using a hybrid communication scheme, we are able to extract like 25 to 40% improvement in performance here. We also made significant improvements to our intranode communication mechanism. So most of the supercomputing systems today are multi-core. So here we see the improvements that we have made to our shared memory-based communication. So if you look at the time taken for intra-socket as well as inter-socket communication, these are the latency numbers and these are the bandwidth numbers, and for intra-socket and inter-socket taken using the latest MVAPICH2 1.9 release on Intel Santibridge systems. Now let's go to some of the newer features that we have introduced, like the non-blocking, like support for non-blocking collective communication. So recently, Mellanox enabled support for the hardware aware or the hardware-based multicast scheme. In our library, we have taken advantage of this hardware-based multicast scheme to implement efficient and scalable broadcast algorithms. Here we see the performance of broadcast on up to 100,000 cores on Stampede. As you can see, with multicast, the performance of like a 4-byte or up to I think up to 64 bytes is the same. It is almost flat. There is no significant increase, and there is a significant difference between the performance of hardware-based broadcast with and without the multicast support. Similarly, this is how the performance varies for a 16-byte broadcast with and without hardware-based multicast as the system size increases. So here the x-axis is in the number of nodes. So Stampede has about 6K nodes, so this is more or less full system size for Stampede. As you can see with hardware-based multicast, the broadcast performance is almost constant. There is no increase, as you can see with the default version. Now let's see some of the benefits that non-blocking collectives can provide applications. So here we study the performance benefits that non-blocking collectives can give for the HPL benchmark. This is for the hyper linear solver from Lawrence Livermore labs. So as you can see, with non-blocking all reduce, we are able to improve the performance of the hyper solver by up to 21%. And with a non-blocking broadcast, we are able to improve the performance of HPL by up to 5%. The more important thing that we can observe here is that we are able to achieve the peak with much lower total memory with like a non-blocking collective as opposed to a blocking collective. Let's look at some of the new fault tolerance mechanisms such as SCR that we have introduced recently. So first of all, what is SCR? So SCR is a scalable checkpoint restart library from Lawrence Livermore National Labs. It can be used for, so basically it has support for utilizing the storage hierarchy efficiently. So as you can see, the farther you go away from the node which is actually doing the checkpointing, the cost as well as the resiliency increases. Using SCR, we can use this hierarchy effectively and significantly enhance the performance of checkpoint operations. So SCR also has support to take checkpoints in an application guided as well as an application transparent fashion. So in an application guided checkpointing, excuse me. the application would provide hints as to when to take the checkpoint. An application transparent checkpointing is the standard system level checkpointing that we all do. So here we see how by using the or by taking advantage of the hierarchy, we are able to improve the checkpointing performance of an application guided case. So this is the checkpointing time taken on like a standard parallel file system, and this is the amount of time that MVAPICH2 with SCR takes for checkpointing the same amount of data. As we can see, MVAPICH2 with SCR significantly improved the performance when compared to the standard parallel file system. So this is the case of an application guided checkpoint. Now let's see how like an application transparent checkpointing works. So this slide compares the performance of MVAPICH2 CR or checkpoint restart on like a standard parallel file system as opposed to on SCR. As we can see, by using SCR, we have significantly cut down on the time taken to write the actual checkpoint to disk. So this was taken with the ENSO cosmology application on 512 processes. Let's briefly touch upon the support that MVAPICH2 has for the hybrid programming models before moving on to what we do for GPU clusters. So MVAPICH2 ideally has it has support for hybrid program models like UPC, OpenSHMEM plus MPI. So what is the advantage of using such a hybrid one instead of just MPI or OpenSHMEM? As you guys know, OpenSHMEM and UPC, those kind of PGAS programming models are good for certain things which MPI cannot do. But the implementation leaves much to be desired for. So our goal is to see if we can take advantage of the years of research that has already gone into the development of MPI libraries and leverage that to implementing and designing better solutions for UPC and OpenSHMEM like PGAS languages. So the current model, let's say if you have to use separate runtimes for UPC, OpenSHMEM as well as MPI, you will need separate runtimes for both. This can result in possible deadlocks if things are not handled properly between the two runtimes, as well as it will consume more network resources. Our approach proposes a single unified runtime for MPI as well as the PGAS programming models. This support is available in the MVAPICH2 X 1.9 release. Now let's look at some of the performance numbers. So here we look at the performance of like a 2D heat transfer modeling application. We also look at Graph 500 and we study the network resource usage for the Graph 500 benchmark as well. We can see that by using the proposed new runtime, we are able to significantly improve the performance of the 2D heat transfer modeling application by up to 34% for 512 processes. Similarly, for Graph 500, we are able to show significant improvements in performance at scale. We believe that as the system size increases, the performance benefits seen here will increase. One point we had identified in the previous slide was reduced network usage. So here we look at the amount of resources required by the runtime to support efficient high-performance communication for the default hybrid GasNet interface as well as the proposed Ohio State hybrid interface. So as we can see, the proposed interface almost saves up to 27% on memory requirements. This as system scale and as the available memory per core diminishes will be significant. We also did really large-scale evaluations of the OpenSHMEM Graph 500 design on Stampede. Although we don't show it here, we do have a number for 16,000 cores, and we see up to 13 times improvement with the proposed design as opposed to the native design. We also have numbers for strong scalability and weak scalability type of runs for Graph 500. As we can see, the proposed hybrid design scales significantly better as the system size increases, as opposed to the default cases. So actually, if you are interested in these kind of results, I would strongly encourage you to attend this presentation, which is happening at ISC tomorrow. It's in Hall 5 between 5:40 and 6 o'clock. So as to get more details. Now I'll hand over to Sreeram to present some of the GPU results.
Thanks, Hari. So what I'll be doing is I'll give an overview of the features in MVAPICH2 to improve MPI communication on GPU clusters. And then I'll present the work that we are doing in collaboration with NVIDIA and Mellanox, taking advantage of the new GPUDirect RDMA feature. So if we look at how the communication technology on GPU clusters has evolved, actually before that, like, many systems are using GPUs, and people couple that with high performance networks like InfiniBand. So with early versions of CUDA, one could not register the same host memory with both the GPU and the network adapter. So what one had to do was to basically do 2 copies before the data can be transferred over the network. So the first copy is from the GPU to the host memory, and then a copy between the host memories that are registered by the GPU and the adapter, and then the data is transferred over the network. Now, what NVIDIA has done is basically they proposed a set of features called the GPUDirect, which basically it's a collection of features which improves the communication on GPU clusters. So the first release of GPUDirect, it enabled common memory to be registered by both the GPU and the network adapter. So what this does is it avoids, or it removes the need for the extra copy in the host memory, but still it will require the copy from the GPU to the host memory and then the transfer over the network. Now, if we look at the perspective from an application, from an MPI application, what does the application developer has to do MPI communication on GPU clusters? So the data has to be first moved from the GPU to the host memory using a CUDA memory copy, and the data has to be transferred over the network using an MPI send-receive operations, and then the data has to be copied to the destination GPU using a CUDA memory copy again. Now, this is simple to do, but it basically the extra copy, it limits the amount of performance that can be achieved on these clusters. Now, the users can also do some advanced optimizations of pipelining these 2 transfers, the CUDA memory copy and the MPI transfer, by basically pipelining the CUDA memory copies and then the MPI send receives using non-blocking MPI operations, iSends and iReceives, before waiting for completion. So this delivers higher performance, but as you can see, it severely complicates the application code. Now, imagine adding the computation into the mix. So you basically have to overlap CUDA memory copies with MPI transfers with your kernel computation. Now, what we have thought is basically, what if the MPI libraries can support efficient communication from GPU directly from GPU memory. So with this, the users will just have to deal with MPI calls and the computation calls, which will make the life easier. So what we have done is we have incorporated this new design into MVAPICH2, which enables MPI communication directly from GPU device memory. So all the user has to do is call the regular MPI send receive calls, and the MPI library internally takes care of pipelining the data movement between the GPU and the host and between the hosts. So this basically ensures higher performance and at the same time higher productivity for the programmer. Now, looking at the performance improvements, so this is from one of the first papers that where we have done work with GPUs in MVAPICH2, and it was presented at ISC a couple of years ago. So if you see, the solution with MVAPICH2 delivers even higher performance than a user-optimized application code. And this is some benefits the scheme brings to end applications. So these are experiments we've done with the LBM, lattice Boltzmann method, and a seismic modeling application called AWP ODC. So we have seen increasing improvements as we went to larger scale clusters. Now, if you look at like collective communication or collective operations is something that are widely used in many MPI applications. So normally collective operations are implemented using point-to-point MPI calls. So if you consider an MPI all-to-all, it's basically translated into a bunch of point-to-point operations in the MPI library. So as I had mentioned earlier, each of these point-to-point operations include data movement and between the GPU and the host, the data transfer between the nodes over the network, and then the data movement from the host to the device on the remote node. So we have already seen how we pipeline these three operations within a given point-to-point operation. But at the same time, it is important to take advantage of parallelism at the collective algorithm level. So what we do is we basically have modified different MPI collective algorithms to basically take advantage of the parallelism at both the algorithm level and the lower point-to-point transfer level. So using this, we are able to achieve even higher performance in MPI collective operations. So this is an example with MPI all-to-all operation, where for larger messages, we gain up to 46% improvement in overall latency. Now, in MVAPICH2, we have these optimizations for all-to-all and all-gather. At the same time, we have introduced hybrid selection of schemes for GPU clusters in all other MPI collective operations. Now, one other important aspect of MPI applications is non-contiguous data movement. This was mentioned by Rich in the presentation in the morning. So if you look at a simple 2D decomposition, which involves a halo exchange, like exchange of boundary information, even in this simple case, the communication in one dimension is contiguous, while the communication in the other dimension involves non-contiguous data. So MPI, to make it easier for the users, provides the feature of MPI data types, which enables users to express non-contiguous data in memory and basically reuse these MPI data types for MPI communication. So these are basically the typical calls that are used for MPI data type-based communication in applications. So the user creates a particular data type to represent non-contiguous data, and basically then uses MPI send receive or any other communication calls to transfer this data. Now, what we have done in MVAPICH2 is to basically optimize the processing of these non-contiguous data in GPU memory. So we use CUDA kernels to basically pack this data before we transfer it over the network. At the same time, we actually pipeline the packing and the data movement to achieve even better performance. So this is some evaluation that we have done with the extended lattice Boltzmann model, which includes 3D decomposition of data. And we see that we achieve increasing amount of performance with more number of GPUs. So we achieve up to 16% or 15% improvement in overall performance on 64 GPUs. Now, one other thing that is becoming common in GPU clusters is each node having more than one GPUs. So in a multi-GPU configurations, in earlier versions of CUDA, if data has to be moved between GPUs that are used by different processes, the data had to be moved from the source GPU into the host memory, then use the standard inter-process communication like shared memory to transfer data between the processes, and then the data had to be moved on to the remote GPU. Now, as the next step in the CUDA GPUDirect technology, what NVIDIA has provided is inter-process communication, using which the data can actually be directly transferred between the two GPUs that are used by the two processes. So this enables a low latency path. At the same time, it being a single transfer, it enables better asynchronous progress of communication. However, this IPC transfer, it requires creation and exchange of something called IPC handles. Now, if you look at the overall picture of performance, the copy through the host, it takes, this is actually with an earlier version of CUDA, I think it is 4.0. So the transfer using the host-based transfer takes around 49 microseconds. But with the new CUDA IPC, the GPU to GPU transfer just takes a mere 3 microseconds. So this is a huge improvement in performance. But if we if we consider the overhead of creation of handles and the exchange, it takes a very high 200 microseconds. So what we do in MVAPICH2 is to basically hide this handle creation overheads using caching and double buffering schemes, so that this high latency does not show up to the end user. So using CUDA-IPC, we were able to significantly improve communication performance on multi-GPU nodes. So for latency, we see up to a 70% improvement in overall performance. And for larger messages, we see around a 50% improvement in performance. And similarly, we see a very high improvement in the overall bandwidth for point-to-point MPI communication. Now, as I said, like CUDA-IPC, which enables a single point of control or a single transfer between the two GPUs, it enables better use of one-sided primitives that MPI provides. So using MPI one-sided primitives, we were able to even achieve higher or lower latencies for data movement between MPI processes. So we see almost a 30% reduction in latency compared to two-sided transfers. And similarly, we see almost a 30% improvement in the bandwidth for medium messages. Now, going on to OpenACC. So OpenACC is gaining a lot of traction in the community right now. So it basically enables users to, or it provides an easier way for users to take advantage of the compute power of GPUs using simple compiler directives. Now, OpenACC also provides a lot of, also provides a library called ACC malloc to control allocation of GPU memory. At the same time, it provides a long list of modifiers to optimize data movement between the GPU and the CPU. So what we have explored is basically how can one use CUDA-aware library like MPI with OpenACC. So one way that the user can do is basically use the ACC malloc library call that OpenACC provides, which basically allocates memory on the device, and then use the device memory as he would use any CUDA malloc memory with a library like MVAPICH2. Now, another approach is to basically use directives called ACC device pointer, where the user can let the compiler take care of the device memory allocation, but then give a hint to the compiler to provide the device pointer to the MPI calls that are being made. Now, these are two ways that one can use a CUDA-aware or GPU-aware MPI library like MVAPICH2 with OpenACC. Now, moving on to the more the hot topic, GPUDirect RDMA. So what we have done with them, so what GPUDirect RDMA is the latest addition to the GPUDirect feature set, where which enables direct access of, basically which enables a network adapter to directly read and write data into the GPU device memory. So this provides a very fast or a fast path for communication from the GPU onto the network. Now, what we have done is we have come up with a preliminary implementation of MVAPICH2 taking advantage of GPUDirect RDMA. So though GPUDirect RDMA provides a low latency path, one runs into issues when you go to like large message communication, especially on modern architectures like Sandy Bridge, where you have very limited peer-to-peer bandwidth performance between any two PCIe devices. So what we have done in MVAPICH2 is to come up with a hybrid design which takes advantage of the low latency path provided by GPUDirect RDMA. At the same time, mix it with the traditional pipeline-based approach, which provides very high bandwidth for communication. We have a demo here at ISC on the exhibition floor. It will be as part of the Mellanox booth, number 326. So please stop by to check it out. Now, looking at the performance improvements, this is the performance we get with for a basic point-to-point MPI operation. So for small messages, we see almost a 70% reduction in GPU to GPU internode communication. So you can transfer data between GPUs on two nodes with just a 6 microsecond latency compared to 19.78, which involved the data movement through the host memory. And for small message throughput, we see almost a 3 times improvement in in message throughput for small and medium messages. And we see an improvement almost up to messages of size 256 KB, beyond which we basically take advantage of the traditional pipelining-based approach. And we see similar improvement with bidirectional bandwidth between GPUs across nodes. Now, this is experiments that we have done with HSG. It's a Heisenberg. It's a multi-GPU implementation of the Heisenberg spin glass model. So, if we see we see good improvements in performance when the application involves smaller or medium messages. So we see up to 40% improvement in latency with a problem size of 64 per GPU. So this basically provides a good case for applications that are strong scaled on larger clusters. Now, one other interesting thing is basically when you consider applications which run multiple process or have multiple process sharing a GPU, when you use the traditional CUDA-based transfers, you incur a huge overhead and context switching when multiple processes are sharing the GPU. So with GPUDirect RDMA, we are able to avoid those context switching overheads because the network adapter takes care of the data movement directly, and we are achieving almost up to a 60% or close to a 70% improvement in performance of the application. And we have seen that the performance improvements increase as we go to more number of processes sharing the GPU. And this is the case especially with the latest CUDA, which provides hyperqueue to enable multiple up to 16 processes more number of processes to basically share a single GPU. Now, so NVIDIA and Mellanox are working to release OFED stack with support for GPUDirect RDMA. So we're planning to time our MVAPICH2 release along with the release of the OFED with GPUDirect RDMA support. Now, to conclude the talk, MVAPICH2 and MVAPICH2X software stack provide a range of solutions to optimize communication on high-end clusters, both in the context of MPI and in the context of hybrid programming. And for clusters with GPUs, we optimize different operations that are provided in MPI, including point-to-point, collective, and data type-based transfers. And we continuously take advantage of the newer features that are being brought out by NVIDIA in collaboration with Mellanox Technologies. And we keep on improving the performance that is offered by the MPI library. So the main advantage is that basically the users don't have to handle or deal with the lower level details. So they still continue to use the standard MPI interface, but get advantage of the high performance that MVAPICH2 offers. So the main goal of our library is to basically provide high productivity, at the same time ensuring high performance for communication. Thank you. I'll be happy to take any questions.